All right, so I'll say it again. So in lecture 13, we started by quantizing free massive scalar field. We saw that it becomes, in momentum space, it becomes a collection of simple harmonic oscillators. We had this creation annihilation operator commutation relations. The Hamiltonian became the following expression. So we mentioned that this combination in the integral, this measure is Lorentz invariant measure. So, and I was intentionally keeping this 1 over 2 omega k in the denominator all the time, just to write down expressions that will remind you of Lorentz covariance. So today I'll be using this notation. I'll try to carry this notation around all the time, which is this curly dk is going to be the Lorentz invariant integral measure, right? This half omega k is omega k is an energy associated with momentum mode k, and we had the creation annihilation combination like this. Of course, it has to be self-adjoint, hence this form. Now, what we did next was that we did normal ordering, which is we came up with a prescription that moved all the annihilation operators to the left of creation, all the creation operator, annihilation operators to the right of the annihilation operator. And at the cost of shifting it by some half. But then there was a Dirac delta that came up because of this commutation relations, right? So there's Dirac delta of 0. Then we mentioned that there are UV and infrared divergences. The infrared divergence has to do with the overall volume of space. So if you put the put quantum field theory in finite volume, these integrals are going to be replaced by sums. This Dirac delta function will become the Kronecker delta. So we won't get this divergence, delta D of 0. That is an infrared divergence. It has to do with long distances and the infinity, the fact that the volume of space is infinite. And then, but there's another divergence that has to do with this integral, right? Over the shift, the vacuum energy. And that divergence is the UV ultraviolet. It's more serious. It shows itself in more physical quantities for such as energy density. So if you calculate energy density, it will be half omega k integrated over this guy. And actually, is there a half? Yeah, there's a half. Integrate over this guy. And of course, that blows up because we have a continuum of momenta, or doesn't have to be continuum, but infinite set of momenta that grow arbitrarily. And the way we dealt with this was that we introduced a regulator, an ad hoc regulator in momentum space. We said that this will, of course, cut it off. But then we said that we need a new principle for quantum field theory, which is physical quantities should be independent of the regulator. We call the regulator the UV cutoff. And then we said this principle is very crucial. It plays a major role in our modern understanding of quantum field theory. All theories are effective field theories, not just quantum field theory, even like beyond quantum mechanics. This is a principle that we stick to. Every theory comes with a natural UV cutoff, and the infrared observables are independent of this cutoff. This is the separation of scale or renormalization principle in quantum field theory. We'll come back to this later in the course, but this is our first interaction with it. So this energy that I'm talking about is vacuum energy. So instantly, based on what I told you, we learned that in quantum field theory, vacuum energy is not an observable because, as we showed, it explicitly depends on the UV cutoff, right? Vacuum energy density is not an observable of quantum field theories. All right, at least in the current formulation that we were discussing. Then we also said that, of course, in quantum mechanics, we could be working in Schrodinger or the Heisenberg picture. But in QFT, we're going to be mostly working in the Heisenberg picture where operators are going to evolve in time. So even though we did canonical quantization and we were talking about X and K vectors, we're going to have to evolve these guys in time, and we're going to talk about phi of X mu, right? All right. We also in the last lecture, we also talked about a Z2 symmetry of complex scalar field. Is the symmetry that swaps phi and phi dagger. If you recall from the Lagrangian density or action, the action was explicitly symmetric under this because it had phi dagger, right? Now, from Wigner's theorem, it follows that any symmetry of quantum field theory will have to be represented as a unitary or anti-unitary on the Hilbert space. So this is going to be represented as a unitary. There will be some unitary operators C and C dagger, C minus one or C dagger, which will actually send phi to phi of X dagger. All right. We said that a complex scalar field, of course, has 2 degrees of freedom. So there will be, if you write it as phi 1 plus phi 2, there will be 2 types of particles. We call them A and B particles. The interesting thing was that both A and B particles had positive energy. However, they had the opposite charge, and we called these the particles versus antiparticles, right? So the Z2 symmetry, the charge conjugation symmetry, is the particle-antiparticle symmetry. All right. Any questions about the last lecture? This brief review of the last lecture. So today we're gonna continue our conversation on quantization by talking about spin statistics connection and quantizing the Dirac spinners. So one thing that you didn't question when I started this whole discussion was that I wrote down a scalar field. We wrote down a scalar field theory, and I wrote down canonical commutation relations, as in A and A dagger will have to commute. Sorry, A and A dagger, the commutator term is 1, right? And I didn't write anti-commutators. Why was that? So the origin of that, this was arbitrary. The origin of that comes from some principle in quantum mechanics. This goes back to Pauli, that says in quantum mechanics, spin is some sort of is an intrinsic property of matter that we cannot really explain, but it exists, right? And there is the observation of Pauli that integer spin particles will have to satisfy commutation relations, and half-integer spin particles will have to satisfy anti-commutation relations. Spin comes in half integers. Half integers and integers will be their statistics is fixed, right? So this is because in quantum field theory, the whole idea of spin came out of representation theory of Lorentz group. We didn't put it in. As a matter of fact, the connection, it also follows that the statistics is also fixed by causality, by Lorentz invariance, by causality. So we're going to see that. So we can prove this statement in quantum field theory. We're not going to do the full-blown proof. We're going to do a baby version of it. And then we'll quantize the Dirac spinner. That will be the discussion for today. In the remainder of this section of the course, in the next lecture, we're gonna talk about discrete Lorentz symmetries, CPT, charge parity conjugation. That's a discrete symmetry of quantum field theory, any local quantum field theory. And finally, we'll end this section with commutators and propagators. All right, any questions about where we're going? So today we're going to make 2 points: the connection between the spin and the statistics, and quantized Dirac spinners. Questions, thoughts, concerns? All right, let's get started. So spin statistics connection. We said in lecture 1 that quantum field theory is an intrinsically multi-particle theory. It's a theory that includes all particles in it. As a matter of fact, generic quantum field theory, in the generic quantum field theory, there might not be a notion of a particle. A notion of a particle is associated with irreducible representations of Poincare group, right? That was the whole discussion of the last section of the course. And then we said, and then from that, actually, it follows that particles of the same field will have to be indistinguishable. They have to be identical, right? Because these are just representations. These are statements about representation theories. You don't get to choose how these, you don't get to distinguish them. This is just, as a field, particles are excitations of the field, and there is no sense if a field has 2 bumps and you want to interpret that are really, really far from each other, and you want to interpret each of them as some sort of particle, you don't get to choose that this one is different from that. There's no sense associated with that. So what we're going to see is the following. You could have your particles, your wave function, two particle wave functions to be symmetric. In quantum field theory, that means that the A and A dagger operator, equation annihilation operator, will have to commute. The anti-commutator should be non-trivial. Or these are the bosonic degrees of freedom. This is the issue of statistics, right? Or the two particle wave functions could be antisymmetric, and this corresponds to what the particles we call fermions, and the anti-commutator should be 1. Do not confuse this notation with Poisson bracket. That was classical physics. We're not going to talk about that here at all, right? So this is the issue of particle statistics. Is it clear? Are there any questions? Now, in quantum field theory, particle spin came about as just some statement about classifying irreducible representations of the Lorentz group. We saw that we ended up with 2 copies of SU2, right, as a Lie algebra. And the representation theory of SU2, if you recall, had integer and half integer spins, because what we dealt with were actually SL to R, SL, well, it was Lorentz group and not 2 copies of SU2. We ended up with integer spins as representations and half integer spins as projective representations, right? So these were all the options that were allowed. This is the notion of spin. Now, the spin statistic connection is the statement that if your particle has integer spin, you should quantize it by requiring commutation relations, canonical commutation relations, CCR. Or if your particle has half integer spin, you should quantize it using anti-commutation relations or canonical anti-commutation relations, CAR, right? This is something that comes up at the level of quantization, right? Spin is just some statement about classical field theory, right? That was just some statement about Lorentz invariance, but now we're going to make a connection between statistics, commutation relations, and spin. So we can prove this in full generality in quantum field theory. You could look up the first volume of Weinberg where he actually does prove this. But what we're going to do today, given the extent of our discussion, what we're going to do is that we're going to show why the particle is a free scalar field bosonic. So when I started quantizing free scalar field, I started with Klein-Gordon equation, right? And the action corresponding to it. And then when I wanted to quantize, I just took A and A dagger to satisfy canonical computation relations, right? So what we're going to see today is that if I had chosen anti-commutation relations, fermionic particles, then causality would have been violated, right? So there's some physics principle which is causality. You shouldn't be able to send signals that propagate faster than the speed of light in quantum mechanics, right? When you put relativity in quantum mechanics, you still have to satisfy that commutation relation. Commutators will have to vanish in space-like separated region. Is this clear? Is this idea of causality violation? Is it clear that causality in quantum field theory means that the commutator of any 2 points, any 2 local operators that are space-like separated must vanish? Is it clear? Signaling quantum mechanics has an interpretation of commutator, right? You can send a signal if 2 operators commute. If you cannot send the signal, to be able to send a signal, you should have a non-vanishing commutator, right? Because commutator tells you about how much you can affect something. Is that right? Is that clear? So being outside of the light cone, you could have correlations. This is very important. Do not confuse correlations with causality, right? You could have correlations between point X and X prime that are outside of, that are space-like separated. No problem. As we'll see, actually. However, you shouldn't be able to send signals. The commutator must vanish. Is that clear? Good. All right. So to show that, what we're gonna do is actually we're gonna show something a little bit more general. The discussion, by the way, this part is borrowed mostly from one of the lectures of Shrednicky's book. If you want to read this in more detail, you can look it up over there. So let's look at our expansion of the scalar field. We expanded the scalar field this way, right? And then the next step that I took in the last lecture was I declared that A and A dagger will have to satisfy canonical commutation relations. Let's not do that. Let's just split this into two terms, call this term phi plus and this term phi minus. The phi plus has only A, phi minus has only A dagger. How do I want it? Maybe I want it the other way around. Doesn't matter. The point is that now these are non-Hermitian things, right? So far, so good? All right. Now, the fact that you want this to be scalar field tells you that under Lorentz transformations, they should transform in the following way. The field should transform in the following way. By the way, when I don't put this vector, I mean, I'm writing an expression which is covariant. I'm writing a 3 + 1 dimensional thing. So I don't always keep track of mu news, right? Sometimes I do, sometimes I don't. At some point, I'll try to uniformize my notation, but sometimes it's quicker if you don't. Then from this follows that these phi plus phi minus that I defined better be scalars as well. They are scalars. All right. So now let's take this N A dagger, define the following notation. The commutator, we're going to call it, the notation is like this bracket plus, the anti-commutator is minus. Why am I introducing this notation? Because the reason is that I want to do a calculation, which is a calculation in one shot, keeping track of both commutator and anti-commutator, right? So here is the commutator, anti-commutator of these two guys, right? Based on the definitions, you learn that this should be just a Fourier transform of the commutator, anti-commutator of these guys. Good. So now let's take two scenarios. Scenario number one is when they satisfy canonical commutation relations. So the plus is 1, right? The second scenario is when they're fermionic. The minus is 1. So I'm just going to continue this way, right? So what you end up with, if you do that, is you end up with the integral over, recall that this notation, what this notation was, this was the Haar measure this was the Lorentz invariant measure integral over momentum, right? Of e to the power of I k x minus x prime. By the way, these are covariant again, x mu minus x prime, right? I'm just suppressing the labels. Hopefully it's clear. You could do this integral, and you will do this integral in one of your homework, and you're going to learn that this is basically m over 4 pi r2. M is the mass of the scalar field. This is a modified Bessel function. And the point of this calculation is to learn that C of R does not vanish at separated points. Right? So that's the observation. At space like separated points. This, first of all, it's only a function of proper distance. Hopefully that's clear. By Lorentz symmetry, this commutator can only be a function of the that, right? Okay, so now let's see the violation of causality. The violation of causality is that if you pretend these two guys are actual fields of your theory, and you look at the commutator, which is the +1, right? You're going to end up with a commutator that's non-vanishing outside of the light cone. Good. All right. What is the resolution? How do we come in peace with this? We say, let's assume we took phi plus and phi minus and added them, and in between we just added some lambda complex variable, complex number, right? Of course, in the phi that I had defined, it was a real scalar field. So this lambda was equal to 1, right? So this is phi lambda. Phi of 1 is my real scalar field. Again, I calculate the commutator anti-commutator, and for phi lambda with itself and phi lambda with phi lambda dagger. In the first equation, I just learned that I get 1 minus lambda squared of CR. I don't care about the anti-commutator here. I want the commutator to vanish when they're space-like separated. Therefore, norm of lambda has to be equal to 1. Is that step clear? So I'm calculating the commutator of phi and phi dagger of lambda. These are my fundamental fields. When x and x prime are space-like separated, the commutator should vanish. Of course, CR doesn't vanish. CR is precisely this bit that I just defined here. Therefore, the only way for this to vanish is that the coefficient vanishes, which is norm of lambda equal to 1. Right? In the case of real scalar field, the case that we just worked out, lambda was equal to 1. The field was a scalar, so this equation was not there to worry about, right? Next, let's look at phi lambda and phi lambda, the commutator and anti-commutator. We end up with this expression. We learn, putting these two together, that we have to make the choice of the commutator for our field phi. So in summary, we learned that causality forced us to have commutation relations for scalar fields. This analysis, I included the lambda in there because you might have wondered, well, for scalar field, we did the quantization this way, but we also did the same thing for Hermitian, for complex scalar, right? For complex scalar, it was the same business. Complex scalar, we still use the CCR relations, canonical commutation relations, right? It won't matter how you define your fields in a sense. As long as what matters is a scalar implies commutation relations, canonical commutation relations. If you pick, there's a full general theorem you could read about in Weinberg, but the punchline is this. I went through this pretty fast, but the punchline is this. If you pick your scalar fields to be fermionic, you cannot satisfy, you will end up with commutators outside of the light cone, which is a violation of causality. So putting quantum mechanics and relativity together will relate spin, which was a classical concept, right? There was a representation theory statement, to commutation relations. This generalizes to higher spin particles, and the punchline is precisely the spin statistics theorem that says spin half integer particles must be fermionic. Integer spin should be bosonic. All right. Any questions? It's a foundational thing. We had to make it, we had to learn about this because now we're quantized, right? The commutation relations matter quite a bit. Questions?
Could you remind me of how the commutation relations of the creation and annihilation operators related to the exchange statistics of the fields?
Ah, very good. Yeah. So yeah. So in the Fock space, you start with the vacuum of the Fock space, right? Then you act with A of K, right? That A dagger of K. That creates a single particle momentum K. Now let's act with another particle like that, right? What have you done? You have created two particles of momentum K, right? You want to know whether, so now this is a wave function of two particles. Statistics was the statement that, so now Of course, you could do various Fourier transforms. Like you could create, you could do it this way. So you could create. Actually, let me do it this way. So integral of e to the power of I k x. I'm just going to be schematic, right? This creates a particle at point x, a single particle. Then you apply this, and this creates a second particle at point y, right? Now you want to know what this is a wave function, right? So to look at the wave functions, you will have to look at the overlap with all sorts of different states, right? Now you want to know if you swap x and y, how do things change? That's this issue of statistics, right? So the answer to your question comes from the Fock space. We talked about how the single particle Hilbert space is embedded in the Fock space as a sector. If you go to the next level, which is two particle states, you discover precisely the connection between commutation relations and symmetry and anti-symmetry of two particle wave functions. And this generalizes to multiple particles. Is that good?
Yeah, thank you.
Of course. All right. Any other questions? Okay. So before jumping into quantization of Dirac field, let's just remember how are fermions different from bosons. So because we saw that free scalar field was just a collection of simple harmonic oscillators, right? With canonical commutation relations, we could have a fermionic harmonic oscillator, simple harmonic oscillator. So the thing that you're more familiar with is bosonic harmonic oscillator. You could have a fermionic harmonic oscillator. So putting them next to each other is very helpful. Let's start with canonical commutation relations between creation and annihilation operators, right? Your bosonic harmonic oscillator, the Hamilton, will have the following Hamiltonian: frequency over 2, A dagger plus A dagger. Of course, using the CCR, canonical commutation relation, I'll say CCR, right? I won't say this a million times again. I can write as a number operator plus a vacuum energy, right? Then what is the Hilbert space? The Hilbert space is defined by first defining the vacuum as a state that's killed by A. Then you act with A dagger to the power of n, and you create n particle states. Good. Now, how is a fermionic harmonic oscillator different? Well, the starting point is to let's call our fermionic creation and annihilation modes B and B dagger. They will have to satisfy Carr algebra, canonical anti-commutation relations, right? From this, it actually follows. So then BB will have to commute, will have to anti-commute, and B dagger will have to anti-commute. From this, it follows that B squared is 0 and B dagger squared is 0. Good? We didn't have such a thing here. All right. So now, if I put a plus sign here, like the previous case, that would be the anti-commutator of B and B dagger. Well, from this equation, I learned that my Hamiltonian would be trivial. It would just be a fixed number. To get something non-trivial, I'll have to pick a different sign. I'll have to pick a minus sign. Whoops. Right? If I do this pick the minus sign, then using the Carr relations, canonical anti-commutation relations, I can write it as omega B dagger B minus half. Now, this resembles the bosonic harmonic oscillator, where this is a number operator. This is a fermionic number operator. There's a vacuum energy, there's a shift, but this one is now minus. All right, how do we construct a Hilbert space? Well, your vacuum is still a vacuum, same thing. It's a state that's killed by B, by annihilation operator. That's why it's called annihilation operator. You can create a single particle, single fermion state 1, right? But then there are no such a thing as two fermions, because if you act with B dagger squared, the same way that you did here, you're going to get 0. So in the simple harmonic oscillator, bosonic one, you ended up with infinite dimensional Hilbert space. Here you end up with a qubit worth of states, 0 and 1, right? So the Hilbert space here is just single qubit. Is this principle clear? And it's forced on you based on by the statistics, right? The Carr algebra. So taking the next step, you'll learn the following. From this, you could extrapolate. Our theory in quantum field theory, after Fourier transform, ends up being, for a scalar field, it ends up being based on the spin statistics connection. Because scalars are bosons, you end up with a collection of bosonic harmonic oscillators, decoupled bosonic harmonic oscillators, right? And on each, so the Fock space will be basically a tensor product of a whole bunch of like harmonic oscillator Hilbert spaces, each corresponding to a momentum mode. Here we're going to end up with a qubit for each momentum mode, right? Is that clear? It's actually more than a qubit, but we'll see because it's a representation theory statement. All right. So Dirac fermion fields in 3+1 dimensions. Are there any questions? Maybe I should pause here. So far, what have we said? We've said that spin decides statistics. By statistics here, we mean there are two choices to make, right? Carr or CCR, CAR or CCR, anti-commutation relations or commutation relations. We said that integer spin means commutation relations, half integer means anti-commutation relations. We're going to now focus on spin half particle, the Dirac equation, right? For spin half particles, therefore, they have to be anti-commuting variables, right? They're anti-commuting. All right. Dirac fermion fields in 3+1 dimensions. We said that the representation theory and the spin representations are dimension dependent. That's why I'm saying 3+1. So we're going to talk about Dirac spinner. Hopefully you recall it's a 4-dimensional representation. We constructed the representation using Dirac matrices. These are 4x4 matrices labeled each. There are 4 of them, each corresponding to index mu, and they satisfy the following algebra. Our Dirac action, spinner action, was an integral over space-time. Of course, it's a local action over a Lagrangian density, which is basically first order gamma mu del mu, right? Psi bar. If you recall, psi bar is just psi dagger with gamma 0, a 4x4 matrix on the right. Good. Is this clear? Hopefully you guys recall the Dirac equation, the Dirac action. This is the action for free Dirac fermionic field. The Hamiltonian, if you want to find the Hamiltonian, you have to do the standard procedure prescription, and you end up with the following expression. You end up with an expression which is an integral over space. So to go from Lagrangian actions to Hamiltonians, you have to pick a particular time slicing, right? Your Hamiltonian ends up being, it's actually the charge associated with time translations, if you recall from another theorem, Noether's theorem. So your Hamiltonian ends up being I psi bar gamma. Now these are vectors, as in gamma I. This dot is, so this notation hopefully is clear that this means gamma I del I, where I've done a canonical splitting like this, right? And this is the thing. This is their Dirac mass. Before, a few lectures back, I was calling this M prime, but I've changed notation. I said when I changed notation, right? All right, so this is your Hamiltonian, and then you learn that pi of psi, the canonical conjugate variable associated to psi, is psi dagger. So it's very different compared to the bosonic Klein-Gordon equation, where the canonical conjugate was phi dot. That has an important consequence. It comes from the fact that the equations of motion for the Dirac equation for spinner were first order, right? Going from classical physics to quantum physics, what we should do is we should impose canonical commutation relations or anti-commutation relations between conjugate variables. Here, the conjugate variable to psi is not psi dot, not the time derivative of psi, but it's actually psi dagger. Therefore, we'll have to impose a relation between psi and psi dagger. We'll get there. But one other comment that I want to say is that if you use the Dirac equation on shell and use the Dirac equation, you could write down the Hamiltonian in the following form: I psi dagger psi dot. You could easily get yourself confused thinking about why this Hamiltonian is first order and in time. All right, so we're going to end up with a fermionic, in anticipation for what we're going to get, we're going to end up with fermionic harmonic oscillators for each k, right? And these are the correlations that we'll have to satisfy. But we said that we had the Dirac spinner had 4 degrees of freedom, B and D's. Each of them has a S variable, which is spin up and down, right? 4 variables total. And they should be satisfying the correlations, anti-commutation relations, right? Which is B of K. So here the important things to keep track of is that we're treating S and R spin variables as independent degrees of variables. Hence, there's a delta of RS. We're also, well, of course, for each momentum, we have a different degree of freedom. Hence, we have a Dirac delta function in K and K bar prime. And this 2 omega K is the same, is reminiscent of the 2 omega K we saw in the case of free bosons, right? So these are the anti-commutation relations that we're going to use to quantize this theory canonically. It's clear? So there are 4 modes. I'm labeling them. There are 2 of the variables are up and down, spin up and down, right? And the other ones are I'm using just different notation, B and D. Good. So in the expansion of the Dirac field, this is what we did for expansion. There is an integral. This is that, recall the notation. This was the Lorentz covariant, the Lorentz invariant integral, right? There is a sum over spin. We put B dagger of S of K. There is U of S of K, which is these were the functions that were supposed to solve the Dirac equations, right? E to the power of minus ikx, D dagger of S, Vs of phi of K. Right? So this is exactly analogous to what we did with the scalar field. We promoted, we just basically introduced these NAE dagger operators, but here we have 4 of them, right? So we have B and D, and then there are the S labels. All right. With these anti-commutation relations, plugging these anti-commutation relations into the definition, into the expansion of the Dirac field, we learn that the Dirac field satisfies the following anti-commutation relations, right? Which is the standard thing we expected and wanted, right? Because the canonical conjugate variable, the canonical conjugate variables are anti-commuting, as they should, right? So this is a good choice. Now, you could write down the Hamiltonian the way that we did it before, just following your nose. What you end up with is, again, these integral over the invariant measure, omega of K. Here you end up with B dagger B. Of course, there's always a spin index that goes for the right, minus D ds dagger. Here, there's something very interesting that's happening. You could, for fermions, it's the same business. Remember, there was a shift by half. That contributes to a vacuum energy. You're going to end up with an infinite vacuum energy, right? So there will be an IR, UV issues, right? We're going to discard all of that. And the way we discard it is using, by introducing the normal ordering, right? So normal ordering, you'll work it out in an example. your homework, but basically what ends up happening is that you can take out the V space, right? Integral over space, and you end up with two number operator. The number operator for the B particle and the number operator for the D particles. This was a notation we used. This was an important convention. We picked this notation because our B dagger and D dagger were creating positive particles of positive energy, but opposite charges, if you recall from the last lecture. Actually, no, I hadn't said that. They create positive energy particles. Any questions about this expansion? All right, now is when I'm going to say that the issue of particle versus antiparticle. This has a global U1 symmetry, right? Which is psi going to e to the power I psi. There's a charge associated with it. It's just a normal ordered psi dagger psi. And just using the standard expansion, you find the same expression as before with a plus sign. Before in your Hamiltonian, you had a negative sign. This is reminiscent of the structure we saw for the complex scalar field. That's why we worked out that example in between the scalar and the Dirac fermion. And then you learn that the charge associated with this is the number operator for B particles minus the D particles. So this, if we are to interpret B and D as particle-antiparticle, they both have the same energy. They both have positive energy, but they have opposite charges. Right? This is very analogous to the story of the complex scalar field. The one particle wave function works out the same way. I just wanted to mention it because in the previous lecture we mentioned it. This phi of S of k is the canonical, is nothing but like the wave function, the one particle wave function. So every time you got yourself confused about what is an interpretation of this mu of S of k, it's analogous. Maybe perhaps it's a better term. It's analogous to the wave function. It plays the role of the wave function. And recall that I had this analogy between quantum mechanics and scalar field theory, right? In that analogy, if you extend that analogy to the Dirac fermions, this is what we're going to get. All right, any questions? Notice that as opposed to free real scalar field, that there was no charge symmetry, there was no notion of charge. Here, spinors naturally come with it. Dirac spinors come with it, right? So there's always this charge conjugation symmetry that is present once you have a Dirac spinor. All right. Very good. So now there is this historical comment, which is, I use this, the way I presented the discussion is the modern high energy oriented. It's because we want the particles and antiparticles to have positive energy and opposite charges. That's what we want. However, historically, this is not how it was discovered, and this is not the way that a lot of condensed matter theorists think about this problem. In relativistic quantum mechanics, this predates quantum field theory, our modern understanding of it. When people try to come up with a relativistic spin half particle, fermion, they basically laid the same foundation that we're discussing here with a difference in notation. So the notation was different because in our notation, we put Bs here. This is the annihilation operator for B particle, and then D dagger for the creation operator for the D particle here. But in their notation, they use annihilation in both. I insist that this is a matter of notation. There's really no distinction between it. We're going to impose the same but we're going to learn something important here. So now, in this new language, your Hamiltonian is the number of B particles. Now I'm going to call these A particles, right? Minus the number of A particles. This means that A dagger creates a particle of positive charge but negative energy. right? This is what in condensed matter or in this old literature that Dirac came up with, these are called holes. The absence of is something that you have to put a particle in so that you come back to nothing. It's removal of a particle. This A dagger removes a particle in a sense, right? It's called a hole excitation. At first, this might seem like a disaster because, well, if you could creating a particle will reduce the energy. That means that your vacuum is unstable. You're gonna just reduce energy by popping arbitrary number of energies. Well, what if you cannot do that? What if you have all the negative energy states are filled? Remember that these are Dirac fermions. These are fermions. So you cannot arbitrarily excite multiple of them. You can of each mode, you can excite only one. You can only put one Dirac, well, one fermion in each state, right? So what if your vacuum is such that all the negative energy states are filled? Then there's no room to excite them further, right? This is what's called the Dirac C vacuum. As opposed to the standard vacuum of B and A, which would be unstable, you could pick a new vacuum, the Dirac C vacuum, where the B particles, they create positive energy stuff. That's all good. So you can take the good old vacuum. But for the A particles, we're going to pick a state which has all the there is a fermion already included in every single possible mode. So you cannot reduce the energy of this any further by exciting. Instead of the particle-antiparticle pair creation in quantum field theory, in this language, what you have is that you can create particle holes. If you normal order this, you're going to end up with expressions of this form, which is now you're counting. You can introduce number of operators, number of particles, and the number of holes, right? I'm just going over this because in condensed matter theory, this Fermi C is a big deal, and like the terminology could be very, very confusing. It's the same thing that we do in quantum field theory, relativistic high energy quantum field theory, except that we usually use a different notation so that our particles and antiparticles, they both have positive energy, but opposite charges. If you read some old paper or books by Dirac, or there's a Dirac book on this stuff, or even Feynman, there is this picture where you think of, well, there is a way of thinking about this, these holes or absence of particles and some pseudo-modern language that's closer to what we're discussing. Now, in this new language, of course, you could just walk through it and you'll learn that your charge is the number of particles minus the number of holes, right? So this arbitrariness, we observed an arbitrariness in our quantization, right? But there was an important lesson for us. In quantum mechanics, it's not sufficient to specify the operators, observable algebra. We also need to pick a ground state. There is more to quantum mechanics than the algebra of X and P. There's more to quantum mechanics than your observables. If your system is infinite dimensional, it matters. You also, to define a quantum theory, you also have to make a choice of a vacuum. That's very, very crucial. Let's think about this for a second. What I'm saying is that observables are not all that there is to quantum mechanics. There is also a choice of state that you have to make to define your ground state or vacuum. That choice is often made for you by requiring you write down your Hamiltonian in terms of your operators, and you try to look at the minimum energy state, right? That's just what we usually do. But what if, well, okay, no, let me not elaborate any more on that. All right, any questions? So in summary, what did we do? We started with, we continued our conversation of scalar field. We first said that there was some important decision that we made in quantizing scalar field that we did not elaborate. We had a scalar field and we chose them to be bosonic. We chose the field to be the particles, we chose the field to correspond to bosonic particles, to create bosonic particles. That choice was consistent and non-arbitrary. It was not arbitrary because the fact that when we say scalar, bosonic is decided for us, is fixed for us. We can't have fermionic scalars because of the relation between spin and statistics. It's fixed in quantum mechanics or quantum field theory, and it's just, if you don't, it's fixed by causality. If you try to violate it, what happens is that you're going to end up propagating signals. Commutated will, faster than speed of light, the commutated will be non-vanishing outside of the light cone. All right, so that was one point. Then we said, okay, so we're going to quantize the spin half particle, the Dirac spinner, right? And therefore they should be fermionic. In free field theory, what you end up with after Fourier transform is a set of simple harmonic oscillator. Because they're fermionic, they're going to be fermionic harmonic oscillator. So we took a fermionic harmonic oscillator, we quantized it, we learned that you end up with a Hilbert space of a qubit. There are just two states, vacuum and an excited state, right? Then we finally switched to our Dirac spinner. We observed a few interesting facts about it. First was that because the Dirac action was first order and derivative, the canonical conjugate variable to psi is psi dagger, and it doesn't have time derivatives. We saw that there is a symmetry, which a Dirac fermion has 4 degrees of freedom that we label with B and D, B particles and D particles, and each of them have 2 spins up and down. So those are your 4 degrees of freedom. That's your count, right? Now, each of these modes will create 2 states. Will correspond to Hilbert space with 2 states, vacuum or 1 excitation. In the notation that we used, we ended up with both of B and D particles having positive energy but opposite charges. Same positive energy, right? Same mass but opposite charges. We interpret them as particle antiparticle. Then there was a symmetry which swaps particles and antiparticles. It keeps the energy fixed, but it switches the charges. It multiplies the charges by -1. That was the symmetry of our. This is the symmetry of our nature, right? Finally, I made a comment about how you could have made a different convention, which in the first look, it might look very bizarre and unstable physics, but then that's because you're interpreting, instead of introducing antiparticles as positive energy, negative charge, you're introducing them as same charge but negative mass. That in condensed matter or old quantum field theory has an interpretation of holes, and this charge symmetry that we're talking about is in condensed matter theory is called particle hole symmetry, right? It's the same symmetry, it's just different convention. There's no new physics. But the physical point I tried to make was that if you try to, with this new convention, try to pick the vacuum of both B and A particles, the whole particles, you end up with something unstable, because you could create a fermion, you could excite a fermion and lower your energy of the your vacuum energy. So a canonical choice we could make is this thing that's called Fermi C. Fermi C is when you fill up all the holes. So all the holes are filled for you, so you cannot excite them further, right? Okay. And then I ended up with a punchline that in quantum mechanics, the choice of state is very important. Any questions? All right. If not, in the remaining 15 minutes, I want to discuss the parity time reversal symmetry. If you recall, this was part of the discrete Lorentz transformations. right? When we discussed Lorentz transformations, we saw that in 4 dimensions, there were 4 parts to it, 4 disconnected parts, and parity and time were taking us in between. My goal here is to make the following comment. Explain physically something that we didn't explain when we discussed symmetries. When I discussed Wigner's theorem, I said a symmetry can correspond to a unitary or anti-unitary transformation. But then when we started talking about our Lorentz transformations, I picked them all to be unitaries. Except for time reversal, that I said it has to be anti-unitary, and I'll just like made an ad hoc comment that pretty much the only anti-unitary anti-unitary operator that corresponds to symmetry in quantum field theory is time reversal. One way or another is related to time reversal. So I'm going to explain that in the remaining few minutes. And this is going to be a segue to the discussion, a full discussion of CPT symmetry, charge parity time reversal symmetry in the next lecture. It's going to be a symmetry. CPT symmetry is going to be a symmetry of any local quantum field theory. That's a longer story. We're going to discuss that in the next lecture. But today, in the remainder of today's lecture, I'm just going to make the point of why is time reversal anti-unitary as opposed to parity, which is unitary. All right, are we good? Is it clear where we're going? So, what is parity? By the way, one important thing to remember is that the distinction between parity, these definitions of parity and time reversal are referring to a basis. Sorry, referring to a slicing of the Hilbert, the space-time, right? So, as opposed to, P and T treat space and time differently, but PT doesn't. PT could be written covariantly as multiplication of x mu by -1. Good? All right, so that was just one comment. Now, let's look at parity first. So parity is, if I'm splitting my x mu into x0 and xi, parity is just putting a minus sign next to xi, right? So in 3+1 dimension, it looks like multiplying your x mu vector by the following matrix. Hopefully it's clear that this is a Z2 group. This generates a Z2 group because if it's an element of the group, you square it, you get identity, right? And this is Z2 group. All right, in the Hilbert space, it will correspond to some unitary or anti-unitary operator. But the way it transforms your scalar field is as follows, right? So it will basically take x mu and just transform it. It's part of the Lorentz group, right? So if it's a scalar, it better transform this way. That's followed by the definition of a scalar. Is that point clear? Actually, because I have that's crucial. Then time reversal is when you keep xi fixed, but you multiply time by minus sign. That corresponds to this matrix, right? So t phi x mu t -1 is like this for a scalar field. Now we find there is room for another possibility. It's perfectly consistent to imagine a field such that under continuous parts of the Poincare transformation, Lorentz group, it transforms like this, but for the discrete part, it picks up a minus sign outside. That's perfectly consistent. That's a choice. We would call that a pseudo-scalar. A pseudo-scalar is a field that transforms as a scalar field with respect to the connected part of the Lorentz group, SO plus D comma 1, right? For the part of the Lorentz transformations that are connected to identity, it transforms like a scalar, like this. But the part of the Lorentz group that takes you from one connected piece to another connected piece, right? These are PT symmetries. For those, you could pick up a minus sign if you choose to. And a field that picks up no minus signs under P and T is called a scalar. If it does pick up a minus sign, it's called a pseudo-scalar. It's a possibility because the Lorentz group is not connected. Is that clear? Pseudoscalars appear in physics, and they're important. Is this distinction clear? Are there any questions about what a pseudoscalar is? So this was just an opportunity to define a pseudoscalar. That's what I want to. Any questions? Okay. Now let's get to the point of why parity is going to be, we're going to represent parity as a unitary transformation, but time reversal as an anti-unitary. Notice that the conclusion from what we're going to make, the conclusion is going to be that PT is going to be anti-unitary. Okay? Which is x mu going to minus x mu. All right. So here's our, unfortunately, the notation is going to be a little bit confusing, and I apologize in advance. This is momentum operator. Momentum is, we write it using as p hat. I apologize. Parity is also starts with p, so we use p operator. Right? By the way, is it clear that p minus 1 is, well, okay, I'm not going to comment on those. All right, so that's going to transform p nu by multiplying it with this matrix. Where is it? Yeah, this matrix. So this is a matrix. It's not an operator, right? This is, so yeah, hopefully this is clear what I'm doing here. And then with respect to t and time reversal, t and t dagger, you're going to pick up this t mu nu. Good. So Hamiltonian is just P0, right? So you learn that Hamiltonian under P will be invariant. However, with respect to time reversal, it will pick a minus sign because time reversal was minus 1, 1, 1, 1. So it will flip the sign of the zero element. All right. That could cause problems. What did we learn? We learned that Hamiltonian is not invariant under time reversal. Hamiltonian positive energy under time reversal become negative energy. Right? It has to do with the fact that energy is a charge associated with time translations. Right? Time translations upwards towards future under time reversal becomes time reversal with respect to past. Right? So it's natural that energy is positive and the energy flips. What matters is not what because it's a symmetry, we want to represent a Hilbert space as a unitary or anti-unitary, right? So what matters is not H and P per se, e to the power, it's not H that should be, to have a symmetry of the theory, it's not H that has to be invariant, it's e to the power of IHT that has to be invariant. Right? It's time evolution that has to remain invariant, not the Hamiltonian. So, of course, because H is invariant under the action of P and P dagger, e to the power of IHT is invariant. Right? Because this means that this is equivalent to e to the power of I, P, H, P minus 1t, and this was just H, so it's invariant. Now, for T, you end up with a similar thing. You end up with e to the power of t, I, h, t minus 1. But if you pick t to be a unitary, this I comes out, and you're not going to get an invariance. This is the origin of Wigner's theorem. Wigner's theorem when he says anti-unitary is also a possibility. If you pick t to be anti-unitary is a thing that complex numbers, when you take them out, they flip the sign. It takes a complex conjugate of it. So t IH t minus 1 will remain IH if you pick t to be anti-unitary. That is why in Wigner's theorem, you're given a choice, unitary versus anti-unitary, right? Here, what we learn is that the requirement, actually, what is telling us that parity is unitary and time reversal is anti-unitary, is the requirement of positivity of energy. That is the requirement. This is very, very crucial, right? It's perfectly consistent to pick a convention in which time reversal is unitary, but your Hamiltonian is not going to be positive. But there's a relative sign difference, right? If you pick that guy to be positive, then parity is not is going to be unitary. Parity is not going to be anti-unitary. It's going to be anti-unitary. All right. So, any questions? This was the last slide for today. So let me just summarize. In summary, what we did today is we continued that conversation of quantization by moving on to the spinors. Spin half particle. Spin half particle, we said that the most general framework we were discussing, there were all sorts of things. There was Weil, there was Majorana, but Dirac was the most general thing we had. It was a 4-component thing in 3+1 dimensions. And we started our conversation by saying that the moment you say spin half, statistics is imposed on you to be anti-commutation relations. That told us that, then we took the Dirac field, we expanded, we wrote down the Lagrangian. That told us that, like, basically in the Fourier space, you're going to get 4 modes, B and D. Each of them have labels up and down spin. Each of these guys come with a label of K, right? Bs of K and ds of K, each of them create a qubit worth of Hilbert space. That's all you've got, right? So for fixed momentum K, you have 4 qubits. That's what you've got, right? And then you have an infinity of Ks, depending on what space you're quantizing, right? If you're in flat space, you have a continuum of M. If you're in on a cylinder or finite volume, you have a discrete set of M, blah blah blah, right? We said that a good convention, the convention that's often picked in particle physics, is such that B is a particle and D is an antiparticle. B dagger and D dagger, they will create particles of positive mass but opposite charges. There's always this charge symmetry because as we said, Dirac spinor is complex field, right? That's just by nature. And we quantized it. What else did we say, actually? We said that, yeah, we talked about particle hole symmetry, the other way of thinking about stuff, blah, blah, blah. And then we ended up on this note that in quantum, when we talked about Lorentz group, the Lorentz group in 3+1 dimensions had 4 disconnecting components, 4 connected components that were disconnected, right? And P and T were taking us in between them. So SO plus 3, 1, the part that was connected to identity, is the part that we focused on. We defined scalar fields and spinors with respect to this guy. But there's a possibility, which is a pseudo-scalar. And a field that is a scalar with respect to the connected part of the Lorentz group, but under T and P, it flips a sign. By the way, can it, instead of a sign, be multiplied by phase? Can it?
No, because if you repeat the procedure again, you should revert back to unity.
Exactly, precisely, right? Because P2 has to be 1, right? So +1, -1 are all the options you're given. So scalar and pseudo-scalar are all you've got, right? Okay, that's very good. So then finally we made a comment about, sorry, this is the beauty of quantum field theory. These things are sort of imposed on you. You don't really make choices. And whatever, in a sense, it's very inevitable. Whatever is allowed happens. You could really classify them. It's crazy. The spins are all that, you know, we could classify all the spins up until when I was a grad student. Higgs had never been discovered. So in quantum field theory, we had quantum field theory up until then. The zero spin particle was a possibility in quantum field theory, but it's never seen in nature. We discovered that too. So it was all good. But anyway. Then we mentioned the following thing, that the disconnected parts, we talked about representing them in the Hilbert space. We said that parity is represented as a unitary and time reversal is represented as anti-unitary because we want the energy to be positive. Then PT is going to be an anti-unitary. And in the next lecture, we're going to say that any local quantum field theory has a symmetry called CPT. charge conjugation, parity, and time reversal. And that thing is going to be an anti-unitary. By the way, anti-unitary. But there's a long history of gradually discovering that PT was not a symmetry, or CP. For a while, people thought CP was a symmetry of nature. There was like all sorts of discoveries of how these like processes in quantum field theory, observable, like observations, scattering processes, creation of modes that led to, were first time observed as a violation of, for example, CP, or like different symmetries, right? So we ended up violating anything that was not really like sacred up until CPT. Turns out that actually CPT in even dimensions is, you could prove it using Lorentz invariance that it must be a symmetry of nature. In odd dimensions, it's a little bit of a longer story. You could still prove it with some assumptions, blah, blah, blah. And it has to do with representation theory. This is all about representation theory, Lorentz group, that treats even an odd dimensions differently. There is another symmetry of nature that does not discriminate between odd and even dimensions. It's called CRT. Charge conjugation, time reversal, and reflection, which is picking any R1 xi and send x1 and send it into minus x1. So in even dimensions, CRT and CPT are the same thing. Anyway, I'll end this rant. There's a long story behind this. Are there any questions? All right, if there are no other questions, thank you so much, guys, and have a nice day.
Thank you.